Hello, my name is Micah Hardyman, and I am a graduate student at Virginia Tech, and this is my presentation on PLM in prosthetics. So, firstly, we're going to go over the state-of-the-art design that we are trying to incorporate into this workflow, and then we're going to go over some common communication barriers and issues that are within the nature of how prosthetics are designed. Then we will be going through the methodology, generally how are prosthetics designed, how are they made, and how does PLM apply to that system. Then we will be going over the fields of research and how that is being done right now in academia. Some of the strengths and weaknesses will then be assessed as far as these different design approaches. Then lastly, how to integrate that into a new workflow, and our conclusion. So, first off, the design that we're working with. This is a prosthetic that I had designed with the intention of being easily printed and suited to any user, with the added benefit that with its new joint design, it is extremely hard to break. Many of the joints in this design can be dislocated, which allows it to sustain a great deal of damage and yet be useful to the user. Therefore, we were wanting to take this design and interject it into the workplace. However, it needs to be ready to go into the workplace and ready to be used by alternate users and also produced by companies. And so we're going to look at some different ways that PLM might be applied to this design and how that it can be reimagined and reincorporated into that system. So, firstly, we'll go over some of the issues and communication barriers that are currently existing within the prosthetics system. And so, first off is the disparity between the CAD languages that the prosthetics industry uses. That namely being that part of it is in parametric modeling software such as SolidWorks and Inventor, and the other is in STL, such as would be found in different modeling softwares like Maya or Mesh Mixer. Some of these different softwares are good at different things, however are usually very incompatible. If anyone has worked in models before, they know that bringing in a STL into a parametric program is usually very hard to work with. You can't really do anything with the part as it's not very well supported by the software. And so there are some issues in that right now in that field. You'll have certain designers designing parts for the human body that are using very organic shapes, and so they work very well in software packages like STLs so that they can be molded and modeled to fit the user completely or to look like a human limb or look like a hand or a foot. And so STLs are very good for that system. However, other parts for a prosthetic are needed as well. You need the hard pieces, such as the structural components, any joints or hinges, almost all need to be made within a parametric software frame. And so you get this disparity between these two different languages, where you have one that's highly organic and highly moldable, that's necessary for that human integration. And then you have the parametric languages that are very precise and very mechanical, but you can't really fuse the two together. And so there is a slight disparity. You'll often see in most designs just a simple threaded connection between those two sides of the coin, as you can't really mix those two via software. Another issue with the collaboration here is the patient confidentiality. So as you're designing through PLM, you're wanting to see the life cycle of the product. You're wanting to see what the end users think of what they have. Unfortunately though, a lot of feedback is difficult in the world of prosthetics because you can't actually contact those people directly. They are protected by law and should be. But however, that does make polling and getting feedback from your users very difficult, and so iterating using PLM is also very difficult. That is one of the issues as we're going through looking at different forms of research, trying to find more information on this, as that kind of break in the loop as far as development processes goes was very obvious. And so moving on to the actual construction of the prosthetic and what that cycle looks like. So here you can see a traditional prosthetic being made. This is a mold of a stump that was cast and is getting ready to be brought into the next stages to make the socket to go over it. And so with this, you can see that the traditional process is to mold, get a mold from the user, usually using plaster Paris or something like that, and then make a cast from that mold, usually in fiberglass or some lightweight material along those lines, and then to test fit it to the patient to see if that part actually is working for the user. So with that, you get certain advantages and disadvantages. Some of the advantages of this design is that you can take the person's anatomy precisely. You get every detail with this method, and that ensures that you don't miss anything when transferring it to the patient back and forth. It's also a very fast process, as it doesn't require any input into a computer. It's simply taking that cast, molding it, and sending it to the user. Now, the second option is, of course, digital, and this is what most of the research you find is going to be over, as casting is a very, very well-refined process. And so in the digital realm, you will first take a 3D scanner and scan the stump, whatever residual limb you have. And with that scan, you will take that in and create a model in some sort of software. Usually, you'll sculpt that out in one of the modeling softwares I mentioned earlier, like MeshMix or such, and you'll make your socket for that prosthetic in that software to mate up with the person. And then you will take that and you will optimize it. You'll send this socket model off to programs like ANSYS or programs like Abacus, and you'll take those in there and you'll do force simulations with that. You'll have both the model of the stump and the socket that you made. You'll mate them together and see with those given materials how those products interact. From there, in a lot of the research material, you'll find different strategies are used for optimizing the socket to see how that it might be best used or best built for the user. And so after you have done that, traditionally what they will do is they will actually take a step back and they will 3D print the residual limb. And then from that, they will use it like they used the cast in the above method. Take this part here, but rather it's 3D printed. And then they will make the part over that in fiberglass or such, as that is the easiest way to manufacture it, and then go for a test fit. This is usually more successful as you have done force modeling, and it caters to not only the user's exact dimensions, but also how that user would put force onto that socket. And so it very much allows for a more streamlined and more comfortable fit for the user. And so we will go ahead on and move into how this is typically looked at in research, since we've been mentioning it so much. And so typically in research, you'll have them testing different advantages of 3D scanning and how that is done. There are some other papers that cover parametric modeling, which we'll get to in just a second. But typically, a lot of the papers are going over scanning advantages. How is it that this method can expedite the process or make it more user-friendly, such as, custom fitting a prosthetic based on geometry and force, something we weren't able to do before. And so a lot of these papers delve into the FEA. They look at shear forces on the socket. They look at normal forces on the socket and how those interplay. You'll get a lot of different dynamics there. One of the other things researchers often tout is how that it is repeatable. You can take this 3D model, modify it, and reprint it. In the traditional sense, when making prosthetics, the mold is destroyed whenever you cast the prosthetic socket. And so you can't redo this at all. And this allows for the user or the producer to make repeatable prosthetics. So say the user breaks the prosthetic they were using. Rather than casting the stump again, they simply use the printed blank I talked about earlier and remake the prosthetic without any issue. This also makes it much more feedback receptive. So if the user says, I really like the socket, but it's catching here or it's pressing too hard there, since this is a digital model, they are able to press, distort, and contort that model so that it suits the user and can have the perfect socket made for them. Now, moving on to the parametric side, there were a few papers that went over the parametric modeling of prosthetic components. Some involving actual implants, others involving orthotics and different applications there. And so we got a lot of information going towards that as well. One of the greatest advantages we saw there is all the files were completely transferable. As these are parametric models, they generally aren't made specifically for the user to emulate any human biology. And so these parts are completely transferable. You can toss some from one prosthetic to another. It's simple threads and bolts putting these things together. And so it's no issue getting this all put together without any custom files or anything like that. So it's a very transferable field and is much closer to the PLM workflow we've been looking at. This allows for people to have custom prosthetics that are very advanced and very receptive to user feedback. This also allows people to iterate across multiple different domains instead of referring back to one master part. Now, moving on to the pros and cons of these different approaches that we have seen in literature and that we have seen in application and we have seen in new methods being used in the workforce. The traditional advantages that we have to speak of are the different advantages you might see with the speed and the customizability for your traditional modeling approach. Of course, that comes with the drawbacks of it being broken and irrepeatable and all the lack of customizability and finite element analysis that comes with using STL models. Now, STL models, while having all the advantages of being easily modified and enhanced, do not have very good compatibility with parametric modeling. And so you can't necessarily mesh the two together. Usually you'll see just a bolt connection. There's not a lot of optimization there that can be done to work those two together easily, at least not for the modelers. It can be done, but it does take time. And lastly, the parametric advantages. And so with that, you have extremely high precision, you have repeatability, you have good ability to optimize that system to the nth degree. However, again, it doesn't look very human. It's not very good for exterior design, and it definitely isn't good for socket design as it can't mesh well with the person, as it is a very, very hard-line geometry. And so with that, we'll move on to integration and how we're going to bring all this information and synthesize it into a useful whole. And so first, when making this new prosthetic for the industry, it's important to keep it modular. As we saw, there are certain programs and methods that simply don't mix, like STLs and parametric models. And so we need to make sure that we keep these parts modular. The socket module needs to be completely separate and integratable with the parametric modules where you'd have the internal structure and any robotic components. You'll want to make sure that the parametric files are all conserved so that those can be passed on to the parent company that takes on this project, allowing for that communication of files and information so well known in PLM. And lastly, products need to be ready to print. They need to be ready to test so that there can be that iteration, that feedback, the modeler and the FEM guy going back and forth, and then that being juxtaposed with actual testing and feeding those different systems back and forth to make a well-optimized design. And with that, that is the end of the presentation. Thank you.